So in this problem, we have a combination circuit with 6 resistors. We know the potential across points A and B is 9 volts. We're trying to find the current through each resistor. We've already done this using the equivalent circuits method. Now let's try it using Kirchhoff's law method. So when we apply Kirchhoff's laws, the first thing we want to do is to identify all the currents in all the different branches. So coming from point A towards point B, there is a current flowing this way. So there's current that we'll call I. This current splits into 2 branches. We'll call this branch I1. We'll call this branch I2. After the current splits here, I1 continues around here. And then current I2 hits a junction right here, so then it splits into currents 3 and 4. Then I3 and 4 come back, they recombine here, comes down here, that'll be the value of I2 again. And then this current splits 3 ways to come down around this way, so let's call these so we've got 3 and 4, let's go I5, I6, and I7. There's all of our currents, and they'll recombine, and then they'll flow out this way. So we want to apply Kirchhoff's laws. So first let's write down our current law equations, which says the total current into a junction equals the total current out of a junction. So for our current law, we have that current I equals I1 plus I2. At this junction, current in is I2, out is 3 plus 4. So I2 equals I3 plus I4. And then at this junction, current 2 is the amount that comes in, and the amount that goes out is 5 plus 6 plus 7. So there's our current law equations. Next we'll do our voltage law equations, which says that the net potential difference around any closed loop has got to be 0. So let's show our loops and let's write the potential for each loop. So let's take this inside loop first. Why don't we grab a different color pen? So let's call this our loop 1. Comes all around this way. So there's loop 1. As we come around this loop, if our loop goes in the same direction as the current, that means we have a voltage drop. So our voltage drop across this resistor using Ohm's law that says V equals IR is going to be minus, because it's a drop, the resistance 21 ohms times the current I1. So there's our drop across that one. We come around to this resistor. We're going against the current here, so this must be a direction that increases potential. So we have plus 45 ohms times the current through that resistor I5. And the next resistor in our loop is the 40 ohm resistor. We're going against the current, so there's a voltage increase as well. So 40 times I3. They all have to be summed to be 0. For our next loop, let's go inside here. We'll come around this way. So coming around loop 2, we have a drop across the 40 ohm resistor, so minus 40 times I3. Then we have an increase across the 60 ohm resistor, plus 60 times I4 equals 0. So there's that equation. For our last 2 equations, we have 2 more loops. So let's come around this loop. We'll come around in this direction. This will be loop 4. Or loop 3. This will be loop 3. So we have a drop across this guy, minus 45 I5. An increase across this resistor, plus 60 I6 equals 0. And then for our last loop, we'll come around this one. And we have a drop across this resistor. So minus 60 times I6. And an increase across this resistor, plus 60 times I7 equals 0. So there are our equations from writing down Kirchhoff's laws. The next thing we have to do is solve it. Let's ask if we can get one more bit of information before we start. This 21 ohm resistor is connected to points A and B, so this resistor must have the potential, the same as A and B. It must have a potential of 9 volts. So let's get that written down here. So we'll do and. So this has current 1, let's call this potential V1. So potential V1 equals 9 volts, and that's the potential across the 21 ohm resistor. So if the potential is 9 volts, the resistance is 21 ohms, we can find that current. That's going to be a piece of cake. V equals IR, so I is V over R. 9 volts over 21 ohms gives us 0.4286 amps. Normally with these things we keep an extra significant digit or two so we don't get too much rounding error. So now that we know the current and the current through and the voltage across this resistor. So that gives us our I1. That's one of the currents we wanted to find. Now we want to go back, work through our equations, and find the different currents. We'll do that in the next video.